So we would like to invite next speaker, and also the wonderful researcher from Italy. So Giorgio Metta is the scientific director of the Italian Institute of Technology. So please.
Thank you. Well, first of all, good morning, and thank you for this beautiful organization. I mean, I'm very happy to be here, to be at ICRA. Great party, by the way. Let me start with a bit of history of my work, and I'll be quick. So it all started with a European project, was called the RoboCub, allowed us for the first time to dream about designing a full human robot. The project started in 2004, so I mean, this very moment is 20 years since we, thought of designing a humanoid to use it for research. I mean, this was the result. It's a full humanoid, tons of sensors, enough degrees of freedom, hands, and possibility of interacting with the environment, interacting with people, and measure the interaction. There's a Ferrari logo there, not because there's any relationship, but because we like to think of our robot as a Formula One car. Not because it's particularly fast, but because it breaks after every Grand Prix. So every single experiment, you have to fix cables to repair the robot somehow. But as I say, that's a research platform, and that's the burden to researchers. Now, my contribution to this research, to this talk, finishes here. Everything else is something I'm presenting work of our PIs at IIT that have taken, in a sense, the legacy of this project and carried out research in different fields. And I'm talking about two topics. One is social interaction, so where the robot is interacting with people, but there's a distance. And the second topic is physical interaction, so where the robot interacts with people physically, there's contact, and there's exchange of forces, etc. Very quickly, the social interaction part boils down to a set of experiments based on cognitive neuroscience methods. Here, I'm taking a narrower view because of for the sake of time. And in particular, I'm talking about the interaction of the robot with children diagnosed with autistic spectrum disorders. We put together an experiment. Unfortunately, or fortunately, it was during COVID. It was a bit of a nightmare to actually do it and carry out the experiments. But on the other hand, allowed us to spend time with the kids, to really entertain them in interacting with the robot. We collected large amount of data, and I can show you basically what we did. We designed an experiment to try to teach the kids perspective taking. This is a skill that is not necessarily developed by the kids autonomously, but if you teach them, and in this case using the robot, they learn and they improve on the specific task. By the way, these people are actors. They're not the real subjects. And you see basically the experiment, there's an interaction with the robot. The robot is manipulating certain cubes. The cubes have letters, drawings. The kids have to guess what is the perspective of the robot. So what the robot is seeing during the play. What happens? What are the results? Well, if you test using, this is a NEPSI-2. It's a standard clinical test for ASD kids. What happens if you test pre and post the long interaction with the robot? The whole thing lasted for an entire semester. Well, there's improvement. The two plots show two of the NEPSI-2 results, and in particular, geometric puzzles and theory of mind. And you see the difference, and you see that the kids are indeed learning. This wasn't enough, so we put together another experiment. Similar concept, a bit more, or a bit funnier in a sense. The robot is pretending to be, or there's a scenario. So this here, the kids are ordering pizza rather than going to the movie theater. There's some interaction also there, but basically the experiment is the same. Again, cubes, again, selection of different objects, viewpoints, all are epitomized by the interaction through the cubes. Here we did a slightly more sophisticated experiment in the sense that we wanted to test a couple of things. One, that learning is actually, first of all, effective, but also lasts long enough. And the other thing is that we wanted to check whether, if we did the experiment with a human control, so we replace the robot with a human, what happens? Is it the same, or do we measure a difference? Well, actually, what we managed to show, and you see it in the plot here, the pinkish graph, you see that if you take one group of kids, you do the experiment, the interaction experiment with the robot, they indeed learn, they improve in the theory of mind measure, and this learning stays there. The second group doesn't get the training initially, it gets it later, and also the second group improves after the 6-month period interaction with the robot. So it seems that it's stable and it's happening regularly, I mean, effectively. The second plot, the gray one, is actually interaction with a human, and nothing happens. I mean, the kids don't improve. Why this is the case? Well, we don't know for real. We can guess that interaction with the robot is more effective because the robot is an easier interaction partner, is more repetitive, which is probably well received by the ASD kids. In conclusion, just to close this part of the experiment, there's improvement to general cognitive skills, like the geometric puzzles. There's improvement of social cognitive skills, like theory of mind. And this is better than standard therapy, as better than just interacting with the humans. Let me move quickly. Again, time is ticking, to the physical human-robot interaction. Here, what we done was to, well, first of all, we assume that a person can be modeled by a person is like a robot, same dynamical equations, basically. It's not true, but we approximate it that way. So once we have a model, we need two things. We need to estimate the parameters and to actually measure the state of the person, so to plug into the model and do some prediction and plug the thing into the controller. What you see here is actually how we do the measurements. So we have joint sensing, that's easy. I mean, we have a sensorized suit full of gyros and accelerometers that can be used to actually estimate the configuration of the body, but we also have tactile and force-torque sensors in the shoes to measure some forces, not everything, but good enough for certain interactions. And what we can do is basically equip people with this type of sensorized suit. And as you can see from the plots, we can both measure the configuration of people interacting with objects, but also their joint torques, which is important both to measure the muscle fatigue, joint stresses, and so forth. Therefore, once we have this measurement, we can design controllers where everything can be modeled basically by the same type of equations, dynamics of the human, the robot, which is easy to measure and calculate, and also the interaction forces. So that we can build controllers that actually implement something like this one. It's difficult to see in the video because feeling forces through vision is a bit difficult, but believe with me, the robot is very naturally following what people are, what our researcher in this case is doing. So pulling, and the robot stands very naturally and with basically minimizing the force that the person has to make to lift the robot. Why is this important? Well, once we have the sensorized suit, what we can do is actually control a robot remotely. This is something we've done at ICRA 2 years ago in London. One of our people in Genoa maneuvering the robot, and at the exhibition we were playing with different robots, all teleoperated. Here, the nice thing is that once you model what the human is doing, you can also compensate a bit for the delay that it naturally occurs in controlling such a long distance. Last but not least, what we can do with teleoperation these days is collect data. And this becomes extremely important for training deep learning models. This is an example, very crude in a sense, but we basically went through a task for whatever number of minutes, collected data, and trained relatively large neural network that includes vision and all the movement data and forces of the robot, and we reproduce the situation to the robot, and the robot behaves and follows adaptively a bit, also the task that was actually trained for. So it's kind of nice, and we are in the condition now to collect indeed enormous quantity of data and train models very, very easily. Let me finish here. Thank you very much, and I would like to say thank you also to the PIs that work on these experiments, Agnieszka Wikowska from IT working on human social robot interaction, and Daniele Pucci working on the controllers and the teleoperation. Thank you very much.
Thank you, Giorgio. Thank you for giving us the long time challenges of iCub interacting with people. So anyone any questions from the floor? Tamim, help me to find that person. Any? Question, please raise a hand. Here. Yeah, now I realized that from the chair it's very hard to find. So thank you.
Hey, thank you for the excellent speech. My question is gonna be, when we talk about human-robot interaction, we always keep a safety distance. So do you think we are going to have a robot we can build intimate relationship with in the future?
Well, why not in the sense, I mean, safety is greatly improved through sensing and through the design of, behaviors that can use that sensing to actually guarantee a certain level of safety. This is happening for simple robots. I mean, it's happening also for industrial robots to a certain extent, so I don't see why not. It's still very difficult. For example, for a humanoid that is walking, I mean, we don't have any guarantee that it won't fall. At this point, I wouldn't, bet on the fact that it's entirely safe. But on the other hand, the robot is in the lab every day and interacting with people. And, in normal conditions, carefully controlled, it still works. I mean, it's still safe enough. Don't know what to say whether in the future we'll see it happening with enough reliability to be actually entirely safe to interact closely with the robot, but I say why not? I mean, we've been improving quite a lot in the last few years with designing robots. I mean, when I started, I think force control or torque control was just a dream. I mean, nowhere to be seen when I started robotics. Now it's common practice, so things are improving.
Thank you.
Thank you.